Hello, good morning or good afternoon everyone. Welcome to Precision Polymer Engineering webinar. Today I'm going to talk about high temperature elastomers in semiconductor applications. So this is the agenda for my talk. I'll briefly introduce myself and my company, and then I'll talk about high temperature elastomers and determining the lifetime of a seal and some plasma benchmarking data. Okay, this is me. I'm Murat Gulkur. I'm Global Product Manager for the Semiconductor Business Line at Precision Polymer Engineering. I've been working for PPE for 3.5 years. I have in total over 15 years of experience in elastomer and semiconductors. My main duties at PPE is to develop semiconductor market for PPE, manage technology roadmap, and manage product life cycle. Now I'm going to talk about my company. Precision Polymer Engineering, or in short PPE, is a manufacturer of high-performance elastomer parts for niche applications. Some industries we serve are semiconductor, oil and gas, and life sciences. We've been around the business over 40 years, and our main manufacturing center and headquarters are in Blackburn, Lancashire, England. We have another manufacturing facility in Brenham, in Texas, United States. We also have sales offices in San Jose, California, Taiwan, and South Korea, and we employ more than 300 people globally. We also have channel partners in more than 40 countries across the globe, and we are committed to deliver the highest quality of elastomer parts to our customers. So now let's jump into the technical bits, and let's talk about choosing an elastomer material. Qualification of an elastomer material is really a great risk, and actually quite expensive for semiconductor fabs and OEMs. The risk is even greatest if the elastomer part is going to a very critical location, for example, very close to the wafers, or if the elastomer part is immersed in plasma. Therefore, knowing the materials to be qualified or to be tested is very important. As Precision Polymer Engineering, we are committed to reduce this risk by supplying lots of information to you. The benchmarking test results help end users to choose right material for their application, and therefore reduce the risk of wasting very precious tool time or contaminating the equipment, and also saving some engineering time. As PPE, we always provide non-biased and fair data to help our customers. Okay, we receive a question quite a lot by engineers. Do you have a generic material which is compatible with all the processes and chemistries? Well, in order to answer that question, we need to ask several other questions, like is it a plasma process? If so, what kind of plasma source? What's the chemistry? What are the gases? Is it a high temperature application? Is it really 300 degrees Celsius or 100 degrees Celsius application? What kind of purity is needed? Is the elastomer part very close to the wafers or touching to the wafers? And more importantly, what's the mean time between cleans, MTBC? It is very important to supply a material which can survive multiple MTBCs. Anyway, the simple answer to this question actually is no. There's no magic material suitable for all processes in semiconductor applications. One material can perform very good in one type of plasma, but the very same material can be very poor in another plasma, for example, fluorine radical plasma. So it's very important to pick the right material for right application, right semiconductor application. Okay, now I'm going to share some information about high temperature elastomers, especially about our new high temperature perfluoroelastomer range, Perlast Helios. Okay, in this webinar, as I said, I will focus on our new material, Perlast Helios G7HA, which is the first material being launched in this high temperature range, having a fully organic formulation with excellent sealing and plasma properties. Within the next 6 months or so, we will launch several new high temperature materials, but this Perlast G7HA is the first material in this range. Anyway, going back to our topic, you can see the datasheet properties of Perlast Helios G7HA on the screen. This material is around 70 Shore hardness with continuous high temperature rating of 310 degrees Celsius. I will talk in a minute about the high temperature properties and testing of this material. But first, I'll talk about compression set. So one of the most important properties of an elastomer seal is compression set. Compression set means the percentage deformation of a test specimen at a temperature under a certain amount of compression. The test piece can be a standard molded button or a standard size O-ring. So as a result of compression set is deformation. So the lower value corresponds to a better recovery of shape. As you can see on the screen, we tested Perlast G7HA against one of the most popular elastomer materials used in semiconductor industry, which is coded as competitor A1. You will see this competitor A1 quite often in my slides. As I mentioned earlier, we present fair and unbiased data, as in this chart. So the compression set value of our material is 20% at 200 degrees Celsius and 51% at 300 Celsius. At the lower temperatures, our material is slightly worse than the competitor, but at higher temperatures, it's slightly better. So no significant difference. But at this point, I'd like to emphasize that the compression set test does not always give correct indication about the sealing performance. Some materials can recover almost fully after compression set test or after compression, but the sealing force generated by the elastomer can be not enough to provide robust sealing in some applications. Later in my slides, I will share the sealing force results of both materials side by side. Okay. Now we'll talk about the composition of the products or materials. As I mentioned in the last slide, G7HA material is fully organic, and we will see some data about it in the next slide. Okay, in order to determine the composition of an elastomer, thermogravimetric analysis, or in short TGA, is commonly used. Just in case if you're not familiar with TGA, I can basically describe it as it's a very sensitive balance sitting in a furnace. And we put a very small portion of elastomer on the balance pan and increase the temperature in nitrogen environment at a certain rate. At 600 degrees Celsius, we turn on the air to burn off all the organics because of the oxygen, and further increase temperature to 1000 degrees Celsius. If the material is fully organic, there will be no residue left after the test. If the material is inorganically filled, then as the inorganic fillers are stable at temperatures over 1000 degrees Celsius, we will observe some residue after the test. So here we tested the same competitor material, and one of our well-known materials, Perlast G67P, and our new material, Perlast Helios. As you can see, the weight loss starts around 420 degrees and then goes down to 0 for all the curves, meaning that all materials tested here are fully organic. There is an interesting point here I need to mention. The initial weight loss temperature of Perlast Helios G7HA material is slightly higher than the other materials, which can be interpreted as this material has better high temperature stability, as you can see on the red line on the TGA curves. Okay, now let's talk about the sealing force data of Perlast G7HA, which is quite good actually. So first, I'll talk about CSR testing. Here you see compression stress relaxation, or CSR in short, equipment. This equipment is quite simple, but it can give very valuable data on the sealing performance of a material. This piece of equipment measures the retention force constantly of an elastomer material at a set temperature. So how do we do the testing? Now let's talk about the test. The standard procedures are described in this ISO standard, but I'll go very quickly. In the bottom image, you see a cell of CSR, which is basically a load cell, capable of measuring force at high temperatures. We place a standard O-ring, a standard size O-ring, between the plates and squeeze it by 25%. And then it starts measuring the retention force, and then we put whole system into the constant temperature oven, which is in this case 300 degrees C. We can use 4 cells at the same time in the oven, which gives us opportunity to test multiple materials at the same time. The graph you can see on the right gives the information about the actual force by the initial force, and you can see a decay in the sealing force against the initial force over a period of time. According to the ISO standards, this test finishes when the actual force reaches to 50% of the initial force. However, considering that the semiconductor applications are mostly under vacuum, even 20% remaining force will be enough to hold the vacuum. Let's now see the actual graph in the next slide. Okay, as I explained in the last slide, the initial force drops by the time at 300 degrees Celsius in this case. As you can see, Perlast Helios material performs significantly better than the competitive material. This Helios material retains a lot higher force than the competitive material for longer period of time. So if we compare the times, as I said in the ISO standards, it says 50% of the time taken as the lifetime of the seal. So if we compare the 50% the time to reach 50% of the initial force, as you can see, we offer almost 40% more lifetime than the competitive material. But as I said in the previous slide, even 20% of the initial force would be enough to hold the vacuum in most of the cases. And if you compare the time to reach 20% of the force, the gap between Perlast G7HA and the competition gets even bigger. Our material offers almost 45% longer lifetime at 300 degrees C in the test conditions, which is dry air. So obviously, the lifetime of a seal is dependent on many parameters such as the compression rate, temperature, groove type, the chemicals used in the chamber, etc. So it's not possible for us to do this test in real life semiconductor conditions. However, having the benchmarking data against a very common competitive material, which is being used in the market quite a lot, gives a very strong indication about the real lifetime of this seal. So, okay, you may remember last year I gave another webinar about the importance of the purity of elastomers, and Precision Polymer Engineering offers market-leading pure materials for semiconductor applications. So now let's go to the data. You can see here 30 element trace metal bulk cache analysis of several elastomer materials using highly sensitive ICP-MS equipment. Actually, these analyses were conducted by a third-party lab who is taken as a industry-leading analytical lab. So the results are not really generated in-house. All of them, are in official reports. And the unit of the results is parts per billion. In other words, nanogram per gram impurity. So if I give an example about the desired levels of purity for critical applications, For example, where the seals are in very close proximity to the wafers or in direct contact with the wafers, the limit set by big OEMs is usually 10,000 parts per billion. For slightly less critical application, it is 25,000 parts per billion. So as you can see here, the total metal contaminants of PPE materials are extremely low. You can see Perlast G67P on the left-hand side in the table, in the chart, which is the market-leading pure material in semiconductor market used for long years. And Perlast G7HA material, you can see on the right-hand side column, it also offers quite pure formulation. So now let's see the data in a table. Which elements do we have? Okay, there's nothing to say, I think, about the obvious purity of G67P. Again, Perlast Helios G7HA is approximately like 170 times cleaner than the popular competitor material, competitor 1A or A1. If you check the right-hand column for G7HA, there is no metal impurity stands out as in the highlighted competitor materials or other competitor materials. Okay, another important property desired to have in an elastomer material for semiconductor applications is the stiction. So after exposure to high temperatures or to nasty process gases or some chemicals, elastomer materials can get sticky. The stickiness of the seal causes waste of time during servicing, as the time required to remove the O-ring will be longer, and in some cases sticky parts can leave some residues in the groove, which will need cleaning before installing the new O-ring or new elastomer part, so which can be really time-consuming. So in order to save some time during servicing, a non-sticky material is preferred by engineers. Now I'm going to show how we tested the stickiness of our material and some competitor materials. Okay, in this test, we have two pieces of polished stainless steel plates, and we place the O-ring in between them and compress by 25% using some spacers. And then we fix the compression by using bolts, and we place the whole jig in compressed state in an oven, 200 degrees Celsius for 24 hours. And then we take the jig out the next day, cool it down for 1 hour, and connect it to our tensometer and remove the bolts. In tensometer, we measure the maximum force to remove the plates away from each other. In the bottom graph, you can see what kind of profile we get, and as you can see, we take the highest maximum force, the peak value, as the stiction force. So now the results. Okay, as you can see, Perlast Helios material has slightly less stickiness than the competitor material. On this chart, Perlast G67G really stands out with the low stiction performance. G67G is our plasma-resistant material, which has advanced nanoparticle filler system, and relatively it has high purity. So if you need a highly plasma-resistant material with very good stiction properties, Perlast G67G will solve your problem. Now we'll talk about the plasma exposure benchmarking results of our new materials as well as the other competitor materials. So let's start with NF3 plasma. We exposed all these rings, you can see, to NF3 plasma in an RIE tool, reactive ion etcher tool, for 6 hours. As you may know, NF3 is one of the most aggressive gases used very commonly in cleaning. Therefore, resistance to NF3 is very critical for an elastomer seal. Again, we benchmarked our fully organic material against the common competitor materials, and competitor A1 is kind of the reference here. And you can see Perlast Helios has significantly low erosion rate in NF3 plasma. Our other materials like Perlast G65HB and Perlast G67G also provide excellent NF3 resistance. By the way, if you'd like to know what these competitor materials are, please drop me an email or give me a call, then I will tell you which one is what. Now let's move to another chemistry. On this slide, you can see ammonia plasma data. Ammonia is widely used in nitride deposition process, and we thought it would be good to check ammonia plasma resistance, as this data not usually presented by elastomer manufacturers. Usually fluorine and oxygen chemistries are very common. So anyway, on this slide, the message I'd like to give is inorganically filled materials perform significantly better than fully organic materials in ammonia plasma. So if you need like highly ammonia resistant, ammonia plasma resistant material, then we'd recommend you to use, for example, G67G or other inorganically filled materials. But this material also has quite low etch rate in comparing to the competitor material. So let's move to another chemistry. You can see another fluorine chemistry, SF6. Again, Perlast Helios material performs very good in SF6 plasma as well. We have the results for oxygen. The same tool, again, different plasma conditions. You can see the RIE oxygen plasma exposure data here. Helios material, again, performs excellent comparing to the other materials. It has lower erosion rate. And just to remind you, to give you information, competitor A2, is an inorganically filled material. So considering that inorganically filled materials have better plasma resistance, our Helios G7HA material has even better plasma resistance than inorganically filled competitor material. Okay, finally, we have direct oxygen plasma data. This test was done in CCP tool, which is a parallel plate capacitively coupled plasma. The formulations our scientists were developed, again, significantly better than competition under ion bombardment. This kind of plasma generates quite a lot of ion bombardment. Anyway, to sum up, Perlast Helios G7HA material has excellent plasma performance in lots of different chemistries. It offers excellent high temperature sealing performance and offers really high purity. Okay. In this webinar, well, I hope you enjoyed our webinar. I've talked about some basic information about perfluoroelastomers for semiconductor industry. We talked about prediction of elastomer seal lifetime using CSR equipment, the importance of purity in high-end applications, and I shared some plasma resistance data, plasma exposure data of some common materials in different chemistries. So thank you very much. And before I finish, I would like to invite you to register our website, prepol.com. On our website, under Engineering Hub, there's quite a lot of information. So you can download like material data sheets, check chemical compatibility of different materials, O-ring sizes, and lots of other things. You can find all these information if you register at prepol.com website. Okay, everyone, thank you very much for attending our webinar. If you have any questions, you can ask now, or you can drop me an email. I will take a few questions before we finish. and thanks again for your time.
Okay, thanks Murat for your insight into high temperature elastomer seals. Now let's get to the Q&A. We'll have about 20 minutes for questions, depending on how many we get. So here's our first question. What is the highest temperature your material can withstand?
Okay, if you're talking about this Perlast Helios G7HA material, as I mentioned in my slides, the continuous operating temperature of it is 310 degrees Celsius. But obviously, it can withstand temperatures up to like 325 degrees for a short period of time, for example, 24 hours. As I said, we are in the progress of developing even higher temperature materials for harsh semiconductor applications or high-end semiconductor applications. Also, we have currently some black non-semiconductor material offering 327 degree Celsius, which is Perlast G75B. We have Perlast G75H. We can offer 325 degrees C. But these materials are not fully organic and not clean enough for high-end semiconductor applications. So thank you for the question.
Okay, thanks Murat. Here's our next question. What is the difference between compression set and CSR?
Okay, you may remember from my slides, compression set test is just the measurement of the deformation, just percentage deformation of an elastomer material under certain circumstances, like, you know, at a set temperature under a compression for a period of time. But when we talk about sealing, in order to provide the sealing, the seal must be energized. So some kind of retention force must be created by the seal. Therefore, compression set material is not measuring the force. It's just the degree of set. But in CSR testing, we measure the retention force created by the elastomer, and it is constantly measured, so it gives a really good idea about the lifetime of the seal.
Okay.
Thanks.
Thank you. Here's our next question. Is the lifetime prediction valid in real processes?
Well, again, I briefly talked about that, but we need a little bit more explanation maybe. In like real-life semiconductor applications, there are lots of parameters which can affect the seal lifetime, like the chemicals used, plasma, type of plasma, the application temperature, even the groove type has some impact. Therefore, it's not easy for us to duplicate all these conditions in our lab to create like-to-like test conditions. Instead, we do benchmarking testing, like what I presented. It gives us an idea about the lifetime of elastomer material compared to the other well-known materials in industry. And as I said, you know, our CSR tests were conducted in dry air, so we can do the test in like immersion in some liquids, but unfortunately we can't generate plasma or we can't pump those semiconductor gases into our chamber.
Okay. Here's our next question. How accurately can you measure parts per billion?
Well, as I said, the test method is ICP-MS, inductively coupled plasma mass spectroscopy. So what it does actually, it ionizes all the atoms, all the molecules in the elastomer material after burning everything. I mean the residue, and then everything in that residue is ionized by using ICP, inductively coupled plasma, in an analytical equipment. And then there's special sensors there. They use like some very advanced. Well, I'm a chemist in education, but I'm not going to go in that much detail. That machine can measure the like time of flight, kind of, and by the time it detects, depending on the time, it shows the molecular weight of the atom. Therefore, it can be, really, really accurate. If you just drop me an email, I can send you even more detailed information about ICP-MS testing, or if you can even search on internet about ICP-MS on optical equipment.
Okay. So we've only got time for a couple more questions. So here's our next one, Murat. Can you tell us what the filler used in the material is?
Well, the material I talked about, a lot, Perlast G7HA material, it's fully organic. So there is no inorganic, no filler material used in it. And I mean, the other materials, if you're asking like G67G, unfortunately I can't give that much information because it's our IP. But for example, other materials, Perlast G67G, for example, I mentioned about nanoparticle advanced filler systems. I can say it's a non-metal oxide nanoparticle, like 35 to 40 nanometer mean particle size filler we use, which is, I can say, in nanoceramic. I can't tell you exactly what it is. I hope you understand my situation. Thanks for the question.
Okay. All right. So here's our last question then. Have you measured cohesive or adhesive strengths?
Well, our Stiction test, I believe, gives, I don't know if it's meant similar to those tests. We've just done the Stiction testing, but adhesive strengths, like, is it something using a third, another like glue-like substance? I couldn't actually fully understand, but we haven't measured those. If you want me to answer this question, can you please drop me an email? Then I'll reply, or I'll give you a call back.
Okay, sounds good. All right, so we're just going to have to wrap up this webinar now. So to find any more information on semiconductor sealing solutions, please visit the PPE website, as Murat gave you the address earlier. And as always, feel free to call or email Murat with any questions or queries. He'll be happy to take those. So thank you for taking the time to learn about elastomer seals and how PPE's solution-minded approach can help you achieve the results that you need from your high-temperature sealing applications. So thanks, everybody, and have a great day.